Hello everyone, welcome to the Cryosphere Pavilion, in person and online. Today I'm Maxence Menton, I'm PhD at the University of Amsterdam, Vrije University of Amsterdam. And today we'll talk about sulfate and we'll have a point of view from indigenous people from north of Sweden. So the first speaker is also Larson. She's vice president of the Sámi Council.
Yes. Hello, everyone, and greetings from Sápmi, but I'm actually right now in Brussels in the European Parliament. So I'm so glad that you can give me the opportunity to participate in your event in Glasgow, keeping up the good work there. And on the topic of the Scopex project that we have been familiar with the last year, I would say that it kind of dropped in our knees in the north of Sweden and in Sápmi in February, where we at the Sámi Council were alerted by our friends and our friend Tom Goldtooth, who sent us a message about testing being planned in Sápmi. That was the first time we heard of it. And it was quite a steep learning curve for us, having been that engaged in this type of kind of climate and environmental technology in that sense. So it's been a steep learning curve, but we quite clear and quite fast came to the decision, and we felt it quite directly when we understood what it's about and what the solar geoengineering technology aims to do. We quite rapidly came to the position that this is not something that we see is part of our chosen future. This is not actually something that we would like to focus that much on. We are focusing on protecting and securing the ecosystems, and because we as indigenous peoples, our cultures is dependent on healthy ecosystems, and that is the basis of our culture, and that is what we need to sustain future generations in our traditional livelihoods. So that is actually our focus, and we see the discussion on geoengineering and solar geoengineering and as actually a detour from what we should be talking about, since we believe that that is not the way to tackle climate change, because it doesn't address the root cause of the problem. So we see it like taking an aspirin without actually going to the bottom of what we need in climate action to actually tackle and combat climate change, and to protect and preserve the healthy ecosystems that and nature that we are a part of and that we are dependent on. So, just having not so much time with you, unfortunately, but I'm really, really happy to be able to participate and to speak with you. I would just, with that, maybe open if you have questions for me on the work of Sámi Council in this issue.
All right. Do we have any questions for Oso? Online, maybe? No. All right. Then I will pass it over to Alasdair from the Stockholm University to give a more scientific point of view.
It was fascinating listening to Åsa talk with us from the perspective of the Sámi and an experiment which was proposed to be done in their part of the world without necessarily asking them. Not all of you will necessarily be aware what she was referring to, the Scopex project, but the Scopex project wasn't a test of sending a balloon up to into the stratosphere with the aim of testing whether it would be possible to deploy small particles high up in the atmosphere with the aim of cooling the Earth. It was a test run that was being proposed to be done there. That test run is not going to be done. I'm going to talk to you about solar radiation management, and I'm talking on behalf of myself and my colleague, Kevin Noon. I'm a geologist, and Kevin Noon is an atmospheric scientist, and we're both equally concerned about solar radiation management. Kevin's going to be joining us online to field the atmospheric science questions, and I'm going to take the geology questions, and we're going to try and work on it together to address this really important issue. Before starting, this might not be necessary, but I'm going to assume it is. I'm going to give you the geological basis of climate, because to understand why solar radiation management does not work, you need to understand how Earth's climate works. And Earth's climate, you can go to many places and hear how complicated it is, but actually it's because what we're doing to the climate is upsetting a geological system, because we're taking rocks and we're putting them in the atmosphere. We need to understand the climate from a geological perspective. There are 3 controls of climate. There is how much heat we get from the sun, solar radiation. When we get more heat from the sun, the temperature rises. That can happen through natural processes such as the orbital path of the Earth around the sun. That actually changes with time. The second thing is called the Albedo Effect. That is how much of the heat that reaches the Earth is reflected back. And you can think of parts of the Earth like a mirror. For example, this entire pavilion is about the cryosphere. The cryosphere is a massive white mirror reflecting solar heat back into space. That's called the albedo effect. The reflectivity of the Earth, the albedo effect, as it increases, the temperature falls. And then we have the greenhouse effect, and the greenhouse effect is the consequence of greenhouse gases such as carbon dioxide, which are very, very good at letting in heat from the sun, but not as good at letting it back out again. The greenhouse effect is rather like a blanket that if you lie in your bed and take a blanket over you, it keeps your body warm, heat in. It's the best way of thinking of the greenhouse effect, is like a blanket. And for reference, every year we emit so much carbon dioxide to the atmosphere that it's the equivalent of wrapping the entire Earth in a blanket of carbon dioxide 0.5 centimeter thick every year. That's why we're making the Earth warmer. So when the greenhouse effect rises, so does temperature. That's enough climate basics to understand what we're going to talk about now. As I said, I'm a geologist. I'm going to take myself into a field, into my comfort zone. I'm going to talk about volcanoes. This is the Pinatubo eruption on the 12th of June, 1991. It was a massive eruption. As not just lava came out, 14 million tons of sulfate particles were emitted to the stratosphere, which is high up in the atmosphere. 14 million tons. So it's not just lava that comes from volcanoes. It's not just carbon dioxide, also these particles. And that had an effect. And the reason it has an effect is because those little particles behave like small mirrors. And just like snow and ice reflect heat from the sun, so do these particles when they're high up in the stratosphere. This is the temperature anomaly, and that's compared with, and that's the same one as the IPCC use, which is why we're sitting up there at 1.2 degrees at the moment. And I want to draw your attention to this tiny little interval in time here, and we're going to zoom in on it. And that's the time from 1991 to 1993. This was the eruption of Pinatubo, and the temperature dropped by up to 0.5 degrees. That's because those little particles up in the stratosphere were reflecting the solar heat back away again. Earth's temperature went down by up to 0.5 degrees for a period of 2 to 3 years. You've just witnessed the increase of the particles in the stratosphere just throughout that year. And I would almost like if that color was white, as it would give you a more understanding of the mirror effect. But what the reason is that the albedo effect of the Earth was increased by between 3 and 5%, because of all those particles. Now, when the eruption of Pinatubo did not only affect temperature, it also affected precipitation, rainfall, snowfall. And we can measure that in different ways. And I've got marked the eruption on there, 1991. One is continental discharge. That's just a measure of the quantity of water running out of rivers into the ocean from the land. And if we watch how that varies over time, we see that there's a massive dip straight after the 1991 eruption of Pinatubo. Another way to look at that is land precipitation. We actually measure how much rain falls, and you see that those curves are not too surprisingly roughly the same. There was a huge drop in precipitation linked to following on from the Pinatubo eruption. So the eruption was followed by record low precipitation in many regions of the Earth. And to give a concrete example, failure of the Indian monsoon. Now, the Indian monsoon is something a climate thing that humans, other species depend on. I'm going to take you to another volcano now. This is Laki, 8th of June, 1783. To give this volcano a date is a misnomer. This volcanic eruption, just like the eruption that's probably now tailing off in Iceland right now, Icelandic eruptions go on for a long time. This one went on for about 2 years. And that eruption pumped 120 million tons of sulfate particles into the stratosphere, cooling the Earth. This is a painting of the River Tyne in Newcastle, frozen, 1783. And that was a clear symbol of that temperature change. But again, it wasn't just a change in temperature that happened. There were also historical records describing a sulfurous, dry fog across much of Europe and Africa. The dry fog caused crop failures, loss of livestock, and loss of life. Many, many church records witnessed to what happened after the Laki eruption. It wasn't just in Iceland. It was devastating in Iceland, but across much of Europe, and there's good but controversial argument that Africa too. Major historical events can be triggered and linked to major volcanic eruptions like these, such as the French Revolution. So, a little bit on volcanoes. So why am I here at the most important climate meeting of the year talking about volcanoes? Because of solar radiation management. And I'm going to talk about solar radiation management, and I'm going to compare it with something which is called carbon dioxide removal. As I'm not going to spend much time on carbon dioxide removal, just briefly, that's ways of taking carbon out of the atmosphere or not letting out in the first place and getting it into primarily rocks. Solar radiation management, I'll talk about in more detail. Solar radiation management mimics volcanic eruptions. We'll look at volcanic eruption and see what it did. It made the Earth cooler. Well, could we do the same thing? So what does one actually do? The idea is to inject particles. We call them aerosol particles, very small particles, such made of, for example, sulfates, calcite, calcium carbonate, that is, alumina, titanium oxide, and various other ones as well, to inject them into the stratosphere with the purpose of strengthening albedo and lowering temperature. And what we can say is that solar radiation management costs less than carbon dioxide removal. I emphasize short term, and that's important that we remember that. It works faster than carbon dioxide removal. Can have an effect in a few years. Carbon dioxide removal is a long, hard-working process. So what's the catch? Sounds like a good idea so far, but it's not. So we've got to be thinking back to the climate basics. Solar radiation management strengthens albedo, the reflectivity of the Earth, whereas carbon dioxide removal and, above all, emissions reductions weaken the greenhouse effect. Let me just give you some numbers on solar radiation management, so we have some scale in our mind. For 1 degree of cooling, you're looking at injecting in the region of roughly what Pinatubo did, 10 million tons of sulfate particles needed to be injected into the stratosphere. Other particles behave slightly differently, but that's the scale we're talking about. Costs starting around about 15 billion euros per year, and requiring 200,000 flights or so per year. Of course, those flights are emitting carbon dioxide to the atmosphere. So there's a catch. It's a bad idea. Why is solar radiation management a bad idea? Let me give you some examples. And our key point that we're going to have to keep in our mind is what we're actually changing. Solar radiation management strengthens albedo, whereas carbon dioxide removal and emissions reductions weaken the greenhouse effect. The climate responds differently. Both might make it cooler, but the climate responds differently. Climate is more complicated than just temperature. Things that happen specifically with sulfates, not necessarily with other particles. Sulfates lead to ozone depletion. Now, maybe some of us in the room can remember back to the ozone hole, which is one of the victories for humans that have shown that we can actually fix stuff. Do we want an ozone hole back again? Continued ocean acidification. I'm going to do a deep dive into that continued ocean acidification as to what it means in the next slide. I said that the climate responds differently. Solar radiation management changes weather patterns, such as where does it rain? How much does it rain? We saw when we looked back at those volcanoes, there was a drop, there was less rainfall after the volcanic eruptions. When you start messing around with weather patterns, there's a lot of things that are put at risk, such as food security, crop yields, water resources. They're understandably linked to precipitation, to rainfall, biodiversity. I'm going to come back to that. And my final slide is going to address something called the terminal shock. I want you to just have that word in your mind at the moment. I'm going to get back to that one. Ocean acidification. Carbon dioxide in the atmosphere is a greenhouse gas. In the ocean, it can convert to carbonic acid, and that makes the ocean acidic. At high emissions, we're looking at fairly major acidification, especially strong in polar waters, and at lower emissions, what we're here at this meeting fighting for, 1.5 degrees, we're looking for a lot less. But these kind of pictures can be a little bit difficult to relate to. So I want to show you another picture, which I can relate to. You see, with solar radiation management, temperatures may be lower, but carbon dioxide continues to rise. And it's especially absorbed in polar waters, as we saw in the previous image. And that's there for tens of thousands of years. That isn't a short thing. Geology is a slow process. The oceans are slower than the atmosphere. Rocks are even slower. But what do these slides show? They show damage that's already being observed to shells in the Arctic and Southern Oceans. And that's at 410 parts per million. Today, we're already up to 10 parts per million higher at 420. Now, I want you to look at that picture and think for a minute what ocean acidification means. What I like to compare with is osteoporosis, where your bones start dissolving. That's what's going on. The shells of these creatures are dissolving. Now, and I want to take you to the terminal shock, because this is perhaps the most important concern with solar radiation management. I'm showing here global warming following one of the IPCC pathways, and unfortunately, it's the pathway that looks like the most plausible outcome of the numbers that are being thrown around for NDCs here in Glasgow. It's not. We're not yet looking at 1.5 degrees. This is this is a pathway called SSP to 4.5, and it shows global warming going up to around about 2.5 degrees by end of century. So I'm taking this as a comparison based on the excellent work from Trysos and co-authors, and I'm going to talk what I mean by terminal shock. You see, if we're going to do this with solar radiation management, we're going to deploy aerosol particles into the stratosphere. That's going to lower temperature. Then we're going to need to continue to do it. But ultimately, we cannot rule out that we'll be forced to stop. We run out of money. We run out of resources. There are conflicts, political reasons. We cannot be certain that we can carry on forever. Now, I'm a geologist. When we're talking about CO2 in the atmosphere, forever is on the order of 100,000 years. That's a long time to commit yourself to a project. So I want us to think about what happens when you start and when you stop. And this is modeling work. I've not done it myself. I'm reporting from the literature, but it's a paper that really touched my understanding and widened my understanding of this. During implementation, temperatures will drop. During continuation, they'll be maintained. And then you've got a termination. And at the point of termination, and this particular modeling experiment says we'll implement it up to 2030, continue it, and then we stop at 2070. The choice of 2070 is arbitrary, but the longer you wait for the stop, the bigger the termination shock will be. Now, the termination shock, what do I mean? Well, once you stop, the carbon dioxide's still in the atmosphere. So all the warming of the greenhouse effect is still there. So the temperature rises very, very quickly. Oops. My wonderful catch. And I want us to look at what that means for biodiversity. Biodiversity is a complicated word. Life on Earth. Now, I'm going to talk about something called temperature velocities, and that's kind of a confusing term. And it's but what we're meaning is how fast is the temperatures or the temperature zones moving on the Earth. And they can be measured in kilometers per year. So your temperature zone, the weather in Glasgow, how long before it moves to Shetland? Measure the distance and divide by a number of years. That'll give you a temperature velocity. Well, critically, estimates from species range movements, as to how fast species can move and are moving in response to ongoing warming, shows that species are seeming to be managing to move roughly 2 kilometers per year. So that gives us an important threshold, which I'm going to put on all of those dials, 2 kilometers per year. When we pass that 2 kilometers per year, biology can't keep pace. And that's when we start talking about extinctions, when biology cannot keep pace with the changes. So, as I've said, recent warming, we're dialing up to roughly 2 kilometers per year. If we now look at warming on the pathway that we're currently looking at, unless we do exceptionally well, which we have to do here at the COP meeting, we're going to pass that. We're going to be up here around about 4 kilometers per year. That means biology isn't keeping pace anymore. Now, if we think of solar radiation management, during the implementation phase, we actually make the Earth cooler and quite quickly. That isn't good for biology. We're actually looking at going the other way at the temperature velocity about minus 4 kilometers per year. Biology can't keep up with change any direction. And if we now were to go and then if we look at the termination shock, and this is for 2070, if we leave it longer, it will be worse. We're looking at a staggering over 10 kilometers per year, over 5 times faster than we have any evidence that supports the idea that biology can keep up. This is a vastly dangerous thing to be doing. And it's the key point we have to think about when we're thinking about climate. It's the speed, not the magnitude of change that harms biodiversity. the speed. How fast is it happening? That's why a terminal shock is such a problem. It's not the absolute temperature, it's how fast it changes. So, solar radiation management, not a good idea. What are we needing to address? We're needing to address the greenhouse effect. The greenhouse effect is largely due to carbon dioxide. This figure is super important. It reminds us something really, really important about what about carbon dioxide. Remember, the carbon dioxide going in the atmosphere, it comes from rocks, oil, coal, natural gas. Those are geological materials formed from living organisms that lived before the dinosaurs. Now, there's a natural way for getting that carbon dioxide back out of the atmosphere. The first thing that happens is ocean uptake, causing acidification, and combined with land biosphere uptake. So that's when photosynthesis, biology is helping. That happens on the 100-year time scale. And for this example, this is a modeling study. It looks at carbon dioxide at 1200. It's arbitrary, the number. What's important is the difference. So we get a chunk of the carbon is removed, maybe about a quarter, gone within 100 years. The next thing is the ocean, and then we're on the 100 to 1,000 year time scale before the deep ocean is helping us, and that's going to take us down to roughly a half. That's over 100,000 years, and then we've got sediments and weathering in the oceans. That's the 1,000 to 10,000 year process, and the last quarter, you're waiting for rocks to dissolve. And I ask you to take a piece of rock and look at it and think how long it takes to dissolve. That's my field of research. I study the reactions whereby rocks dissolve, and it is slow. That's what ultimately removes carbon dioxide from the atmosphere. So what is the solution? We reduce emissions to get ourselves in line with 1.5 degrees. That is the only way out. The CO2 is going to be there anyhow. Whatever we manipulate with albedo, the CO2 is still there, still going to be haunting us, still there to be dealt with. So this is why we need to focus on carbon dioxide, because carbon dioxide is, I add the word to make the geologists happy, almost forever. For us humans, it's forever. So to conclude, remember that solar radiation management cools the Earth by strengthening albedo, but it does not weaken the greenhouse effect. Volcanic eruptions tell us about the risks of solar radiation management. We can look at them, so that means we have evidence in the geological past to tell us what we can expect when we start manipulating albedo. Solar radiation management puts, for example, food security, water resources, and hugely importantly, remember, we are custodians of all living things, life on Earth at risk. You just listened to an Indigenous speaker talking about the life around them that we are here to protect. We're not allowed to mess around with this stuff. And critically, solar radiation management locks in the risk of a terminal shock. I cannot tell you when that terminal shock will be. But unless we're going to carry on for 100,000 years, I can tell you it will be. So just as Åsa told us, to use the analogy of aspirin, solar radiation tackles one symptom of climate change, temperature, one symptom. But it does not take on the underlying cause, greenhouse gas emissions. They are not changed by solar radiation management. They're still there. And as I hope I've been able to illustrate today from this review talk, solar radiation management has dangerous side effects. Thank you very much for listening. I'm hoping that Kevin's online to help me with questions. This is a diverse subject, and the questions can go outside my field, so I will be sending back and forth to Kevin. Thank you. And Pam too. Oh.
Kevin's presentation now. and then we'll take the questions for both presentation.
I think Kevin's just going to...
Yeah,
he's just going to answer questions. He's going to do a
no,
presentation.
He's here.
Yeah, but is he doing a presentation? I think he's just answering questions.
All right. Well.
Hello, Kevin.
If you have questions, please welcome to the microphone to ask your questions.
Hi, Alasdair.
And Alasdair. Thank you.
Hello.
Hello.
Yes. Hi. Thank you. That was great. Chris Dunn, University of Colorado. This is just hypothetical. That was a great presentation. I completely agree, but I'm just throwing it out there. You're talking about 100,000 year time frame. Assuming humans still exist in centuries or 1,000 years, it seems likely that we could potentially come up with technological solutions to remove carbon from the atmosphere, remove carbon from the ocean in that kind of vast time frame. So it seems like a different. It seems like at the same time to be saying some of these numbers, we'd have to be sort of comparing technological development, which is really hard to do in a future forecast, and something obviously we should rely on. But it is, I mean, these are huge timeframes to just look at the rate at which technology is developing. That's all I have.
I think it's. Thank you for that comment. Absolutely, technologies have different rates. We have a low-hanging fruit when we're talking about the climate crisis. We have emissions reductions. That we do not, the technology is there for finding alternative energy. The solution is so simple. Gambling on, again, putting 100,000 year timescale for geology and gambling on a future solution. I'm not a gambler. I don't know if you want to comment, Kevin.
A quick comment is that technologies, we're speaking about different kinds of technologies, I guess. One of those technologies is taking carbon out of the atmosphere and putting it someplace else permanently. And we have to have that kind of technology to stay within 1.5 degrees of global warming. And that's an absolute must. And it's pretty much an absolute must if we want to keep temperature rise to 2 degrees or less. So some of those technologies are going to be necessary. So yes, we do need to develop them. But I guess from my own personal point of view, I guess, is that we can't, we have, I think, a hope that there will be a silver bullet. There'll be a technology that's going to save us all. And I think Alasdair just said that some of those solutions are already existent. We just need to implement them. But I think technology is a tool. It's a wrench. It's a screwdriver, and we have to be able to build something with that tool rather than seeing the tool as the solution. I don't know if that makes any sense or not.
Thank you, Kevin.
Any other questions? Yes.
Thank you very much. First, thank you for informing me about the French Revolution reason, because I'm French and I've never been taught that before. So that was interesting. So
actually, my colleague Pam informed me about that.
Oh, really? Yeah, it's not in the French history books somehow. We talk about like solutions to deal with carbon. So with your knowledge, what will be like maybe the 2 or 3 most promising solution you will think might save us?
Number 1, emissions reductions. Number 2, emissions reductions. Number 3, emissions reductions. We will have to complement that with CDR to make the 1.5 goal, but emissions reductions now is going to make that a lot easier. Kevin, do you want to add?
No, nothing, just to agree. Again, we have, if you think about this, one of the things that we need to do is make transformations in some important sectors, like our transportation sector, our energy sector, our agricultural sector. And a lot of what we hear is that those transformations, they're too big, they're too expensive, we don't know how to do them. But think about this. We've already done those transformations in 2 generations' time. When my grandparents were around, they actually rode horses. That was one of their primary transportation mechanisms. They didn't have nuclear power when they were around. They didn't have solar power. They didn't rely as much on oil back then as we do now. The agricultural sector was completely different. The Green Revolution hadn't happened in my grandparents' time. So between my grandparents and me, we have transformed those sectors that we need to transform. Again, smarter. So the idea here is that many of those transformations we know about already, and Alasdair is said already that in terms of what to do, it's stop emitting carbon dioxide to the atmosphere, figure out how do we produce our energy, how we get ourselves from point A to point B, and how we produce the food that we eat without emitting so many CO2 molecules.
Thank you, Kevin.
Do we have any other questions? No? Sure? Online? Nope. All right. Then we'll close this event. Thank you very much for coming. The next event is at 4. It's about just transition for North Sea oil. Thank you very much.
Thank you very much. Thank you, Kevin.